Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience, who would be curating the RealSci_Nano Twitter account.
Hello everyone, today we have with us Jessica Boland, who is a lecturer in functional materials and devices.
Thanks, it's nice to be here.
Great, let's dive straight into the research and your research journey. So how did you end up in your current research field?
Yeah, it was quite a long journey into the research field. I wanted to be a professional ballerina first off, but it didn't grow tall enough. So I'm only 5 foot if you meet me in person. So that was kind of out. And then I started looking at what subject I wanted to study, and I couldn't decide between classics, so Latin, Greek, Roman history, and maths or physics. And in the end, one of my maths teachers gave me the advice of going to do physics because it's applied and you keep asking me why for everything and it's annoying. So do physics and you won't get bored. So I did. And I started out studying for an undergrad in physics at the University of Exeter, and that was really fun. I had a year in industry, so I spent time working with Hewlett-Packard Labs in Bristol, and it was a pretty cool research project that I got to do. So I got to try and make a reflective liquid crystal display. So you take a Kindle, and at the moment it's black and white, and that's a reflective display. And trying to do that in color using liquid crystals. So making a new color Kindle. And I found that awesome because it was applied. I could see where everything was going towards a device. I spent a lot of time in a clean room at the start, spin coating these liquid crystals, coating them everywhere, and trying to make some nice mirrors that could go in this device. And then you took that kind of mirror that you made out of liquid crystal, and then I got to make a prototype device of a cell that worked and changed color. I really loved that. I still have videos of it somewhere, and it's probably hidden, the prototype cell, in a box somewhere in my attic as well. But making that prototype device was really, really fun, and that's when I kind of knew that I wanted to do something applied in a research field, and I was definitely an experimentalist. And then I went back for my master's project at Exeter and got to also get hands-on in an experimental project in something a little bit different. This was looking at spoof surface plasmons in the microwave range. And they kind of have applications in cloaking devices. So if you wanted to kind of cloak a plane from microwave radar, then plasmonics is one way that you could do that. And that's what I was looking at during my master's. And again, had a great time and really enjoyed it. And then was looking to carry on being in the lab, being hands-on, and decided, well, let's do a PhD. What's the harm in that? Let's carry on. PhDs are hard work, as we know, but I wanted to look at these types of materials that I was interested in. So the liquid crystals, these nanomaterials, plasmonic materials, and how I could use them in a device. And I found out about terahertz radiation, which is the non-contact way of looking at electronic properties of nanomaterials. And I thought, this sounds really cool. I can look at these different types of materials and hopefully use them eventually in a device. And that was my PhD in a nutshell. I haven't really looked back since. So I'm still using terahertz radiation, and still looking at nanomaterials and still trying to make everybody's devices much more cooler and energy efficient and better. And that's how I fell into this current research field that I'm in.
Okay, that sounds really interesting. Starting with the ballerina and also this colorful Kindle. I want to know more about that later. Um, it, could you explain how and where does your current research? You already talked a little bit about that, but how does it fall or fit in this big picture of materials or nanoscience? Where does it fit?
Yep. So if we want to have 21st century devices, so we're coming up to the limit that silicon technology can give us at the moment. So we're reaching physical limits. So we need these next generation of devices that are more energy efficient. And to produce these devices, we really need to use quantum effects now. And those quantum effects are at the nanoscale. And we
Right.
want to integrate devices. So I talked a little bit about plasmonics, photonics, electronics, spintronics might be words that you've heard, and it's all different ways of transferring information in a device. And we need to start to integrate them all together. And in terms of how we do that, we need to be able to design these materials from an atomic scale. So
Right.
take an atom, grow a material, but design these electronic, spintronic, optical properties, all the properties that are important for a device at that length scale, so that we can build custom tailored materials. And once we do that, we can really say we have a device application. Here's my material that is designed specifically for this device. It's going to increase device performance.
Right.
And my research is in between those two stages. So I characterize the materials using terahertz radiation. So I get lovely, beautiful, high quality materials from collaborators
Right.
who want to know about the properties of those materials. I characterize them using terahertz spectroscopy and microscopy
Right.
and feed that information back into the collaborators that grow the materials, but also the collaborators that then use those materials into a device. So I'm kind of the middleman, if you like, between material optimization and device development. And that's where my area of research fits in.
Right. So you're basically an integral part if a material or any kind of technology needs to be transferred or can be transferred from the lab bench to the market shelf. You play an integral part there, right? Did I summarize
Yeah.
it? Yeah.
Exactly, yeah. So, yeah, providing new information about new materials that we can then use in devices. One example of that is looking at, say, semiconductor nanowires. They have potential for many device applications.
Right.
So, nanowire-based solar cells. Also, they can form modulators of terahertz radiation for communication.
Right.
But if I want to use one of those nanowires, I want to know that I'm using the best nanowire that has the highest electron mobility.
Right.
And those properties are important, and those are the properties that I help characterize using terahertz spectroscopy.
Okay. Sounds like super interesting work. And I'm pretty sure you're involved in doing a lot of cool experiments and characterizations. So the next question I can already imagine is going to be tough for you. Um, if you had to pick one research project that you're most proud of, or the most fun or quirky one, I know it's difficult. Could you pick one that you're most proud of and explain it to us in the section we call "In Other Words," please?
Of course, yeah. I think my favorite research project was creating a nanowire-based terahertz modulator.
Okay.
So, this started by looking at gallium arsenide nanowires. Gallium arsenide is quite a well-known material,
Right.
and these nanowires are about 50 nanometers in diameter and about 10 microns in length. So they form a kind of long stick, a quasi 1D structure,
Right.
and they have some anisotropy in them. So if you shine terahertz radiation at them of a certain polarization, if the polarization matches the nanowire axis, so they're both aligned with each other, then the nanowires absorb a lot of terahertz radiation. So you get an off signal, if you like, a minimum signal.
Right.
If I rotate the nanowires by 90 degrees, so now the polarization of the radiation is perpendicular to the nanowire axis. They form like an X shape if you looked at the polarization in the nanowires. Now terahertz can be transmitted through it. So you have a maximum signal, which is an on signal.
Right.
And we now have a binary signal, an on and off, to modulate terahertz radiation.
Right.
Just by rotating nanowires or rotating the polarization of the radiation as well. And one of the cool things about this was we can actually switch this modulation of the terahertz on picosecond timescales. So that's 10 to the minus 12 of a second. So really quick timescales. And we can do that because we can optically excite the nanowires. So we put in a photoexcitation pulse that's infrared. And then we have lots of free carriers in the nanowire. And those are the free carriers that are absorbing that terahertz modulation.
Okay. That is so cool.
Yeah, and you can switch the polarization of that optical beam to switch your modulation on and off. And that's how you can have a terahertz modulator on picosecond switching speeds. But why I think it's my favorite project is because this could be the route to ultra-fast wireless communication. So if you want to have your wireless communication at terahertz speeds, at the moment we're at gigahertz speeds. So if you want it 1,000 times faster, terahertz speeds, you need some of these terahertz modulators to be able to do that.
Right.
So it's my favorite project because I got to characterize the nanowires and then make them into a device that could make wireless communication faster.
That is so cool. I can imagine why you picked this as your favorite research project, because picosecond, when you say it, you don't really get the feeling for it, but when you think about it, it's 10 to the power minus 12 of a second. That is really fast, really fast.
And what was quite cool about it was it's a faster switching speed than graphene. So graphene can give you a much higher modulation depth. So the difference between your on and off signal is much bigger. But at the time that I did this research project, it was just nanosecond switching speeds. So it was quite nice to be able to use these nanowires to get better switching speeds. But there's still work to do, which is why it's also one of my favorite research projects, because there's still ways that we can actually improve the performance of those nanowires as terahertz modulators as well.
Right.
Yeah.
Okay. So did I understand it right? The gallium arsenide nanowires are faster or better in this sense than graphene. Did I understand
The switching speeds, in terms of switching speeds. But the current ongoing work is to look at different types of nanowires. So we were using gallium arsenide. Can we use different materials, for example, to make that performance better? But one of the beauties of this was that we're exploiting that like directionality of the nanowire, so that 1D shape, and just switching it round to give you some modulation, which was quite nice.
It's like a toy at a nanoscale, isn't it?
Yeah, that's how it feels to me, playing with the nanomaterials to get some cool properties.
I have another follow-up for you. Is there any candidate for femto?
Yeah, that's a lot harder to get. Yeah, femtosecond switching speeds. Yeah, definitely a lot harder. So,
Okay.
but yeah.
Okay, let's fix the picosecond one. Let's bring that in our everyday life, and then we can think about the femto one.
Exactly. And there's always the common joke that it takes 20 years once you've made a prototype to get anything to market anyway. So there's some
Right.
time before we see terahertz modulators, I think. So
We just have another 20 years, or at least 10 more years, to think about the next big thing, the femto, go into the femto level. Okay,
yeah.
fantastic. This sounds really cool. I'm already pumped about to know about your favorite research project, and I hope you will go into the details when you're curating the Twitter account. Yeah?
Yeah,
Okay, super.
definitely.
Let's move out of the lab a little bit and go towards the other parts of usually most of the researcher's life, which is teaching. So, do you teach? And if you do, which courses would you like to talk about?
Yes, I definitely teach, and I'm in the midst of actually making a new course at the moment. So I'm in the Department of Electrical Engineering,
Right.
and one of the key courses for all of the undergraduates is about electronic materials,
Mm-hmm.
and that's the course I'm currently teaching. So this kind of looks at how you would build a material from an atom all the way up to a bulk material,
Right.
and how you get the material properties that we see. So, for example, if you take a metal and you take an atom, looking at metallic bonding, what properties does that give us? Also, taking insulators, what type of atomic bonding gives us an insulator? How does the crystal structure that we see influence the electronic properties, the mechanical properties of these materials?
Mm-hmm.
And then once we kind of understand that and we've got our metals, our insulators, our semiconductors, how do they behave? So how does their electrical conductivity change if we heat them up, for example?
Mm-hmm.
If we put lots of defects into our nice, beautiful crystal, what happens to our electrical conductivity then?
Right.
Those types of questions, and that's what I'm currently teaching at the moment.
Oh,
So, yeah,
that sounds really cool. I hope you can.
very related to my research, as you can see now. So,
Yeah, but it still sounds good. I hope you can give us some sneak peek into what you're teaching the students. This sounds,
definitely.
yeah, this sounds amazing. So let's go back to the research experience. I hope your research experience so far has been wonderful and will continue to be wonderful in the future as well.
Thanks.
However, if you have to pick, like if you had.
I think, yeah, I was thinking about this quite hard. I think one of the things that's really, really important to me is to have an inclusive, accessible research environment for everybody, so that everybody doing research doesn't experience any barriers stopping them do that research.
Mhm,
Um, that everybody feels welcome in that environment.
mhm,
Everybody feels safe, everyone feels included and like they belong there. So I think that's probably my biggest wish,
mhm.
for that inclusive, accessible environment.
Right.
I think another wish would to be to have a good work-life balance. So I personally am quite strict with my time, so I don't work on the weekends. I try not to work on evenings, but that's not always the case for everyone. So I think I would like the research environment to have an ethos towards that balancing between work and life balance,
Mhm,
because there's always so many things to juggle, um, especially with COVID and lockdown. I think a lot of people have had to juggle childcare, working from home, all of these things, and we've had to start to be more flexible to different working hours. And so I think I'd really like to see that stay, so that we are promoting well-being, looking after mental health, and having that work-life balance.
mhm.
Um, and I think the final wish is probably something everybody asks for, which is time to be creative and go into the lab because there's a lot of time pressures. So there's a lot of juggling between research, teaching, admin. And so I think I would always want to be in the lab a lot more. But I think everybody would love to spend their time in the lab, full stop. Maybe not 24/7, that doesn't go with my work-life balance.
Right.
But yeah, more time in the lab playing with my lovely lasers.
Few hours every day. A dose every once in a while is good. Healthy dose.
Exactly. Yeah. So
Okay,
I
that sounds
think
good. Yeah, go ahead. Sorry.
I was going to say that it's really good because I actually have some really lovely postdocs and PhD students that get to go in the lab and perform the experiments better than I probably can now. So that's quite nice. But it's always good to go and spend some time in the lab with them, just playing around.
Yeah, I can imagine. I would love to go back to lab. If I could, I would just love to go back to the lab. Like 1 hour a day. That's fine for me. I'm okay with that.
Yeah. I am missing my lab at the moment in lockdown, but soon.
Oh, fingers crossed. Fantastic. So all three wishes, including your accessibility and inclusion for everyone, um, work-life balance, and more time in the lab, I would always support that. So I hope that we are working towards it, especially the accessibility part, because work-life balance. I think people are starting to be more mindful of it.
Hmm.
Um, and creative in the lab, I guess that depends on individual. So I hope it is working once we
Yeah.
can go back to the labs. And speaking of future, what are you most looking forward to in the next 3 months?
Definitely going back to the lab, so, of course. But I recently had a lovely new terahertz microscope delivered. So I'm quite excited for getting that installed, set up, and doing the first couple of measurements with that. And
Right.
that system is awesome because it can do this non-contact electrical characterization with 30 nanometer spatial resolution. Yep, it's pretty cool. So you can map the electrical properties on these nanoscale length scales. And you can also go down to low temperatures, so down to around 10 Kelvin with this lovely microscope. So I am so excited for setting that up properly and also looking at some materials on these new length scales.
That sounds so cool. I'm looking forward to those pictures. I'm assuming it won't be set up by next week, but in the future, the you can definitely share some videos and some pictures. That sounds fantastic,
Definitely.
especially the mapping part, especially at low temperatures. I think that is amazing.
Yeah, yeah.
Um,
I'll definitely share some pictures.
Super, super. So, Jessica, before we let you go, what we want to understand from you is what are the big challenges faced by the field of materials or nanoscience from your perspective? What are the big questions that the researchers are trying to answer?
Yep, I think that's a great question. And I think I would go back to that the problem that we're facing of reaching limits of Moore's law and Moore's law slowing down. So having to look at new materials, advanced functional nanomaterials, and really being able to design a material from the atom all the way up to a device and having that feedback loop between nanoscale growth and functionalization. So, tuning these electrical properties or optical properties by doping on nanoscale length scales,
Mm-hmm.
for example,
Right.
then being able to characterize them on the same length scales, these nanometer length scales, so that we can have custom tailored materials for devices. And I think that's one of the main challenges now in the material science, having that control over optoelectronic properties at these nanometer length scales.
Mm-hmm. Okay. All
But
right.
we're going to get there,
We're
definitely.
yeah, of course.
We're going to get there.
I
We're
mean,
already.
Yeah,
Getting there.
we are working towards it. We have this amazing, wonderful microscope that is delivered to you. So we are gonna get there, absolutely. But
Yeah.
that is really interesting because I don't know a lot about the field of optoelectronics and spintronics. I've only heard little bits and pieces at conferences and seminars. So this is a very interesting perspective. That's what is the main challenge, to have this feedback loop of sorts. So thank you very much for sharing that, and thank you very much for taking us on a fun ride to learn more about your research and your research journey. And we are very much looking forward to and excited to have you on Real Scientist Nano.
Thank you ever so much for having me. I'm excited.
Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.